Okay, this is 7.1.3, still in chapter 7.1, making our way through. And this has got some three things that are actually related to each other, and that is how radii and chords can talk to each other and work with each other. So there are three theorems here. I'm going to do a quick sketch of what the proofs look like of each of these, and again, these will be great tools down the road as we look at pictures and figures that have radii and chords in them. I'm going to start over here with the orange circle and saying that a radius that is perpendicular to a chord will bisect the chord. So the radius that I've drawn here is perpendicular. You can see that that's the case. I'm going to get my little pen going. We've got a little 90-degree angle there. Let me see if I can draw the color here a little bit better, blue. And we've also got so a radius that is perpendicular to a chord will bisect the chord. How do we know that Hj, right, will be equal to Ji over here? Well, you can imagine that right away, like all circles, we've got radii. There's one right here and one right here. They are equal to each other by definition of the circle. And we also have the famous reflexive property, so dj equals dj. These two triangles become congruent by not ASA or side angle side, but these are two right triangles. And so they are congruent by hypotenuse, leg, if you can remember that. And that allows us to get Hj equaling Ji by CPCTC. CPCTC. One of our favorites. Okay, down to the purple. We've got the idea, a radius that bisects a chord, right? So the radius is bisecting the chord. You can see that I've got a couple of lengths here. So CF and FB are clearly equal, 3.21 each of them. And if I move it around, whoops, if I move these things around a little bit, everything stays the same. I've created them this way. So no matter where I put this, I have the chord is split in half. But the radius that bisects a chord will be perpendicular. How do we know that the radius is going to be perpendicular here, right? So we need to prove that. And again, we rely on the fact that there's a radius here and a radius here. They are equal to each other, right? Maybe you've already seen this. You can see ahead. AF is congruent to itself, and part of the given is that this piece is equal to this piece. So these two triangles are congruent by side, side, side. You guessed it. And therefore, the two angles, AFB and angle AFC, are congruent and they're adjacent. And we know that congruent and adjacent angles that make up 180 degrees must both be 90 degrees each. Okay? So that's the quick proof there. Finally, over here on the left, we've got this idea, the perpendicular bisector, right, of a chord. Remember, the perpendicular bisector of a segment is perpendicular at its midpoint. So two things are true here. We have the perpendicularity and we have the midpoint, okay? And we're trying to prove that this perpendicular bisector goes through the center. And the way we do that is, again, we put in the famous radii, right? They're congruent to each other. And now we have, let's see, two triangles that are congruent. Oh, we don't have it. That's actually right. What do I messed that one up. I should not have. There we go. We have to, all we know here, see, I messed that up, and that's okay. I can show that to you. We've got a perpendicular. We've got a bisector, right? The question is EL equal to EK? Because if it is, then E becomes the center. We're trying to prove that. So these two triangles, right, without assuming that they're equal, these two triangles are congruent by side, angle, side, right? So side angle side helps us here. And that tells us that, in fact, we have these two pieces, right, become congruent. These are CPCTCs. And therefore, E must be the center of the circle because those two become radii. Okay, so those are 3 helpful theorems related to circles, radii, and chords.